Okay, so here we have a typical elemental analysis problem. You have a chemical compound that's referred to as a hydrocarbon. It contains hydrogen and carbon. Typically we write the carbon first by convention, and no other elements. What are we looking for? Empirical formula and molecular formula. How do we get there? Well, we need experimental data. Now again, one of the biggest stumbling blocks, I think, conceptually, of when you're working on these problems is you ask how. How do I get these values? So these values, which are the gram values for the elements, you actually have to go in the lab and do an experiment to do that. This value, the molar mass, is done by a different form of experiment as well. So don't overthink some of these problems. You have to be given some information to start the problem, to move forward. So we have a hydrocarbon. It has carbon and hydrogen in it only. You're told that the mass of carbon is 9.226 grams. The mass of hydrogen is 0.774 grams. Again, determined by experiment. Through a different experiment, probably mass spectrometry, you're told that the molar mass is 78.1 grams per mole. So now we need the empirical formula and then the molecular formula. The molar mass is going to allow us to convert between them. When I have a chemical formula, it's a ratio of atoms. The unit is in moles. 1 mole of hydrogen to 1 mole of carbon, or 10 moles of hydrogen to 15 moles of carbon. We're given grams, so we must convert from grams to moles. All right? And I'm going to go through this relatively quickly because it's really about the setup, the math. You can do that with a calculator. So 9.226 grams of carbon, and we want moles of carbon. Okay. I just used the molar mass from a periodic table, grams of carbon. In this case, the value that I'm given has 4 significant figures, so I should use the molar mass of carbon so that I do not lose any significant figures. For these particular problems, if you round, you will screw up the problem because they are very sensitive. So in other words, if I rounded this to 0.8, when all is said and done, I could be very, very far off from the final answer, the correct final answer. So keep all your digits until you finish the problem. So this value has 3 significant figures. Okay. When I do an analysis dealing with hydrogen, I use the molar mass of 1 hydrogen atom, not H2. So I'm going from grams of hydrogen to moles of hydrogen. Okay. Now, at this point, moles of hydrogen, I've got a fractional value of hydrogen and carbon. You must use the lowest whole number ratio between them. In other words, saying that my chemical formula is carbon 0.7681 to hydrogen 0.7679, that doesn't mean anything. So we clear the fraction. You can see these values are very, very close. So I'm going to divide both of them by the smallest. So I'm using a different color to show that. Okay, so I divide each, And it essentially gives me a 1-to-1 ratio. Okay. Again, this comes out exactly to be 1. This comes out to be 0.9997. So it's basically, it's 1. So this 1-to-1 ratio is my empirical formula. All right. But we want the molecular formula. Now, to get molecular formula, we need that one more little bit of information. The molar mass. If I did not give this to you, then the problem would be over. All we could solve is empirical formula. To do this, what we need is we need to figure out the ratio of CH that gives us a molar mass of 78. There are a couple ways you can do this. You could simply say, if I double this, if I triple this, if I quadruple it, and so forth, what eventually gets me to a molar mass of 78.1. It's not wrong, it's kind of tedious to do it. The better way to do this calculate the molar mass of 1 carbon plus 1 hydrogen atom. And when you do that, it's 13.019 grams per mole. You can kind of do this in your head. Carbon weighs about 12, hydrogen weighs about 1, so it should be 13. 13 and then change when you do it properly. So now what we need to do is figure out that ratio. I'm going to go ahead and put in the units simply because you'll see that they're going to cancel, and we're just going to end up with a number. That is what we scale by. So this is our empirical formula, our unit that we have to scale up. If this value was 13, if I take a step backwards, if this value was 13, we would be done because the molecular formula would be the same as the empirical formula, but it's not. So when we find this ratio, this comes out to be basically 5.99. So we round that obviously to 6 because it has to be a whole number ratio. So our molecular formula is going to be this times 6, which is going to be, put it right here. So we times this by 6, which is C6H6. So that is my molecular formula. You have to have empirical formula first, then you need your molar mass to get to the molecular formula. It is possible that the empirical and molecular could be the same, but we know that's not true because, again, when you calculate the mass of a carbon plus a hydrogen, it's 13, not 78. But 6 times 13, basically, gives me 78, so that's how I get this ratio. So this is the kind of problem that it's very easy to get frustrated with because you have to go from grams to moles, but now it's in a fractional value, so you have to convert that to a whole number ratio, so that gets me here. Then you have to do another calculation to get this mass, then the ratio, and there we go. So it's something that any one of these steps you should be able to do. Putting them all together is where you have to be patient. You have to understand that these type of problems are going to require some thought. You're going to have to sit down and think about, okay, if I want to get from here to there, it's going to take a little bit of a grind. So whatever you do, don't get frustrated and just say, well, I'm going to say I have 9 grams of carbon and 0.774 grams of hydrogen, and then make that your ratio. That's without a doubt the most common way to get this type of problem wrong, to not even do the calculation between grams and moles, and try and use this ratio. But again, if you go back to the concept of the mole, that ratio is not going to be valid as far as chemical formulas are concerned. So take the time to work through each step of the problem, knowing that it's gonna get you where you need to be, but it's not going to be something you can do in one step. These type of problems, again, are not difficult in their mechanics. They're difficult in the concept of how to go from here all the way to there. All right, if you notice, again, there's no differential equations, there's no calculus. It's a thought process, and if you don't practice this type of problem, you'll be dead in the water during an exam. I can guarantee you that.